Дякую. Дякую, що запросили мене до Львова в цей важкий час. Но жаль, я не могу розмовляти українською і перейду на англійську.
So, I hope you can hear me and you can see my slides. It will be my introduction to quantum information, and we meet today on April 25th. However, in fact, we celebrate the Quantum Day on April 14th. So thanks for coming here. So do you know why somebody decided, I even do not know who, to choose this very date, April 14th? It's kind of a matter of choice. However, symbol of quantum theory is the small h bar, reduced value of the Planck constant. And in some units, electron volt times second, the value is somehow like small number, 10 to minus 15, but first digits are 4.14. So you can translate it into April 14. Therefore, they decided to take such a date. But of course, it's kind of more or less arbitrary, because in other units, we can also use another unit to celebrate it on April 25th, which is equally legitimate. And this is the picture from Krakow. I will not go too much into technical details, but I would like to give you a flavor of the quantum theory and quantum information. But first, let me show you a picture. You can see two gentlemen. I will tell you they are talking, and in fact, you can guess they are talking not on quanta, but they are talking on mathematics. In fact, it is Otto Nikodym on the left and Stefan Banach, I presume you know the name, on the right. And they were talking in Krakow during the First World War in summer 1916. I will come to this story later, but first, I will ask a very simple question. If you take a 10-year-old boy and ask him a question, what happens if he kicks a ball? Of course, he will know that the ball will roll along the grass, but eventually it will stop. Furthermore, if you buy an ice cream and wait a bit, what will happen? Every child will answer, the ice cream will melt. This is clear. But now you can ask questions why it happens, or try to describe those issues in a quantitative manner. So you can ask a question, how far the ball will move, or how fast ice cream will melt. So if you ask a question, what is physics? So physics is a skill to produce some important, reasonable approximations to answer such questions. Of course, we know many different questions we can try to answer in such a more physical, scientific way. And now, if you ask a question, so we know what is physics. Sorry. I did something wrong, just. Or maybe, here, sorry. Yes, so just a second. So this is physics. Now what is, thank you, the quantum physics. It's the same physics, but physics adapted to the very small objects. How small? At the size of an atom, which is really small. So for hydrogen atom, it is some number 10 to minus 10. It's really a very, very tiny number. And then why we use the word quantum? Because we discuss physics at the energy of light. And the energy of light is quantized, and the standard unit of energy is just energy of a single photon, which is just proportional to the frequency. And now you see h, this Planck constant is just here proportionality constant, or if you use the omega frequency, then this h over 2 pi, and this is the value we started with. Now look, this constant was used already 125 years ago to consider the famous problem of black body radiation. And now this is the quantity in units of action. It's position times momentum. And strangely enough, since 2019, h bar is used to define a kilogram. So, you know, many years ago, kilogram was defined in Paris by a piece of metal which weighs like this, but now they decided to change, and the kilogram can be now defined just adopting a known value of Planck constant. So due to uncertainty relation of Heisenberg, we can celebrate in 3 years 100 anniversary of this famous relation. We cannot determine the position X and the momentum P of an electron of any other particle with very good precision. So H bar tells us about uncertainty of such a measurement. And therefore, quantum mechanics is a very strange science. It's not deterministic, it's probabilistic. So we cannot even try to answer the question where electron is localized in the phase space, but we can ask a question, what is the probability to register a particle here or there? Therefore, probability is the key method working with quantum particles with microscale. Now I'm going to discuss information. What is information? Information, wow, you can convert slides, music, messages into sequence of numbers and numbers into sequence of bits. Bits is a binary unit. So bit is just 0 or 1. Bit is binary unit. So classical information, in fact, is a sequence of bits. So all this presentation and my voice can be represented as sequence of bits. So we usually represent bits by 0 or 1. Or for instance, you have to have a physical realization. So you can write 0 or write 1, or you can choose, let's say, spin up or spin down, or you can choose one state of an atom or other state of an atom. So in the quantum version, we have such a strange notation. This means that spin is up, for instance, and we use, instead of such a 0, such an object we call a cat. Technically, in mathematical language, is an element of some Hilbert space, even Banach space. But here is only just a decoration of the 0, while here is 1 for another state. But now something strange happens. The set of quantum states is larger than classical. Classically, if you have 1 bit, there are 2 possibilities, 0 or 1. 2 bits, there are 4 possibilities. 3 bits, there are 8. They form such a cube. For 4, they form a hypercube. In general, we have 2 to the n possibilities. They are just corners of such a hypercube. But in quantum physics, there's this famous particle-wave duality. So particles sometimes display properties of a wave, and waves display effects of interference. So if you have interference in phase, there is a constructive interference. In the opposite phase is destructive. So therefore, if you have a slit, a wave, now 2 slits, you observe here at the screen, there are fringes. So you have sometimes constructive interference and sometimes destructive. And therefore, not only waves can display interference, but also quantum particles, also photons, but also electrons. And now a question, what is the quantum state? So quantum state, I denoted here by such a head of this vector, and usually I use the letter psi, is, well, in some sense, a mathematical tool which allows us to compute probability of results measured. Sometimes we also use the word wave function. So in fact, it's the same state, but it depends on some variables. So now look, classically, we had a bit binary unit, 0 or 1, nothing more. So spin up or down. But in quantum world, we use the word qubit, which is an abbreviation of, look, qubit is quantum bit. So quantum binary unit. So it's also binary. You have states 0 and 1, but you can have a different kind of superpositions of those 2 states. So the state psi is, mathematically speaking, we use 2 complex numbers, C0 and C1, which are normalized as much as this. And now it's easy to show that such state represented here by 2 numbers corresponds to a point on the sphere. So classically, we have only spin up or down. And in quantum theory, we are allowed to use any position of orientation of spin. For instance, such a point is at the sphere. The sphere is called Bloch sphere. By the way, those Bloch papers were written after the Second World War in 1946. It corresponds to a superposition of states 0 and 1. This is another superposition with another phase. So classically, we have only 2 points, like 2 poles of the sphere. And in quantum theory, qubit can take any position at the sphere. And here, look, there's a word geometry. You can take it literally. So in a sense, the space of a qubit is like our Earth. You can study geometry of this space. And the normalization implies that probability is conserved. So probability of finding the quantum state in state 0 and 1, denoted here by P0 and P1, they sum to unity. Well, to summarize, classical states are represented by the poles of the spheres. All other points are quantum, and those at the equator are, in a sense, the most quantum. They represent symmetric superposition of both states. We say that we can transform any state like North Pole into any other by rotating the sphere, which mathematically is done by a so-called unitary matrix. Unitary because it does not change the length of the vector, it's only a rotation. Oh, so we know what is a classical information theory. Classical information works with classical bits. So what is quantum information? More or less the same, but we work with qubits. So in principle, you could say, you have here, instead of a bit, 1 qubit here, 1 qubit there, 1 qubit here. So like different copies of this block sphere and different orientations of the vectors. This is correct, but this is not enough. This is more complicated than that because you can have different interaction between different qubits. So what is the advantage of studying quantum? Why quantum information is in some sense more interesting than classical? The answer is simple, because first, we have larger space. Classically, we have only poles of the spheres. Here we have a larger space of states allowed, and we have a larger set of operations available. Therefore, we can perform such tasks which are not possible in classical world. What is interesting if you consider now bipartite systems? Well, if you have like 2 objects, like classical objects, we have 1 spin here, 1 spin there. They are classical, they are not correlated. 1 spin shows here in this direction, another shows this direction. This is all what we can say classic. However, there are also some other states which basically describe interaction between those 2 objects. And mathematically speaking, we say that a state is product or separable. It can be written, it's called tensor product, but basically it means that you have 2 different objects which do not interact. And action on one subsystem does not change. Here it changes, you see? So they are somehow coupled. It does not change the state of the other system. But quantum theory allows also for existence of other states which are called entangled. Definition is simple. Any state which is not of this form of a tensor product is entangled. So in a sense, it's like just superposition, but for 2 bipartite systems. And the most famous state, well, now it's always called Bell state. But this idea goes back to the famous paper of Einstein, Podolsky, Rosen from 1935. Looks like this. What it means? 0, 0, it means 0 on the left subsystem, 0 on the right, and superposed with 1, 1, which is in some sense very strange and very, very non-classical. Because what it says, I have 2 objects, I measure 1 object, and by measuring whether this spin is up or down, I can predict the result of measurement on the another particle. So look, I have something in my pocket. I have 2 dices. Okay, they are standard dices from 1 to 6. Can you imagine that I have such dices that if I throw them, they are still in the air? And then if I, let's say, look at the result here, I can predict what was the result there. So classically, it's not possible. But quantum mechanics, this is just the idea of entangled state. That performing measurement on one side, they were in such a quantum state that looking at the first dice, I can, with probability 1, predict what will be the outcome of the second dice. So of course, classically we can hardly imagine how it looks like. I have another model, but of course, this is only a coupling of two classical objects. It's not entanglement. But in some sense, you can think there is kind of maybe not invisible thread, but some consequence of interaction between those two objects, which explains correlations. So in short, what is quantum entanglement? It is correlations between subsystems. And in the Bell state, there are perfect correlations. Measuring one subsystem, I can infer what will be the result in the second measurement. Is it clear? This is the most important notion. So correlations between subsystems due to interaction, quantum interaction or previous interaction or preparation of such a state before. Well, so the famous example in some sense is even earlier from Schrödinger. Maybe you know the story of Schrödinger cat. So in a sense, the idea is, here is just this famous Gedanken experiment, that there is this radiation which breaks this poison, and then the cat is dead or alive. So in some sense, you can have such a Bell-like state that the poison is not broken and it's alive, together superposed with poison is open and cat is dead. And of course, you don't observe such cats in such a state in real life. However, there is such a cat-like experiment of even done in France by Aroche already more than 15 years ago. What I observe here is like probability distribution, and two peaks correspond to superposition of quantum states in two different states. So this is like cat alive, cat dead, and they are superposed. So in the classical world, we don't observe such cats. Why? Okay, I will explain it later. Okay, in principle, they may happen, but probability is very unlikely, goes to zero. But the smaller object, the more likely it is to create and observe such effects of quantum entanglement. So here is a nice story from American journal that I have. This is Mr. Schrödinger, good news and bad news concerning his cat. He's partially alive, partially dead. And another picture I like very much, quantum mechanics for skiers. So maybe you know it. So look, here is one skier which looks into another one. And you can see there's kind of special kind of interference effects, which also you don't observe so often. If you go skiing, you don't see such tracks very often. Why? Wow, in principle, such superposition effects may happen, but not at our scale. At least I have not seen them yet. Well, but you cannot see them concerning macro states, but you can produce such states in micro world on a smaller scale, for instance, working with photons. So here is a nice example. It's the same sphere, but now not a block sphere. We call it here Poincaré sphere because it represents polarization of light. So here is circular polarization left and right, and here are vertical and horizontal polarization. And the experiment goes like this. You have a blue photon, which is highly energetic. It goes onto a nonlinear crystal. Then there are two rise of red photons, and they are correlated in such a way that it may happen that, okay, here we have V stands for vertical, H for horizontal polarization, or otherwise. And what you observe, it is just here at the screen, you can observe such correlations or anti-correlations between polarization in the first and second line. So, in short, entanglement, there are correlations between results measured by two different detectors. It is analogy to Schrödinger cat. However, those existence of entangled states does not violate relativistic rules because there are correlations between results of a measurement, but you cannot transmit information in a superluminal way. And the last important point is, I claim that entangled states do exist, so you can really generate them in the lab and confirm that they are there. However, they are fragile. Why? Because they are destroyed by any interaction with environment. And the larger object, the stronger, let's say, decoherence. Therefore, we do not observe in real life such quantum effects, but they can be observed in the lab. So now, what is quantum information processing? We take quantum information, which is decoded in such a state. For instance, here is this first superposition state. Here is entangled state of two particles. And we want to apply to perform such some useful tasks. For instance, I will mention here like quantum teleportation, quantum computing, quantum cryptography, and many others like metrology, but you can also have quantum games, quantum finances, or very popular recently, quantum machine learning. Let me mention now quantum teleportation. What is teleportation? I wish to take this object, like, for instance, any object like dice, and do something with it such that it appears here again. So classically, of course, it's not possible unless you are a magician. In quantum, the following is possible. If you have entangled state between Alice and Bob, you can take this state C to be teleported, and after some tricks, so measurements in the Alice lab, you can destroy the state on the left-hand side, but you can generate the same state in the Bob lab. So this is a paper by Bennett et al. From 1993, and making use of this Bell state, which displays correlations between two subsystems. Alice can send her unknown, what is important state to Bob, and can be reconstructed by Bob. So if you ask a question, what is teleported? We don't teleport electron or photon. We teleport quantum information, because this quantum information, which was encoded in the state of Alice, will be exactly reconstructed in the lab of Bob. So this idea from 93 was first realized in an experiment in the lab by Zeilinger, using exactly this technique of photons and nonlinear crystals. So here there was generation of such two entangled states. Here was first state, which was to be teleported, measurement, and here Bob could create such a state. Later in Spain, by the way, so in Spain they managed to, in 2012, achieve teleportation from La Palma to Tenerife at the distance of 133 kilometers. And a few years ago in China, they managed to teleport quantum state to the satellite and back at the distance of 1,000 kilometers. So I think nowadays Chinese are best in this business. This was teleportation. Now I will mention a little bit about quantum dynamics. So we can take a state and do something with it. For instance, classical gate NOT is what? Is putting this spin from 0 to 1. So inverting the spin. But quantum mechanically, you can do some other operations like square root of NOT. Is such operation, if you do it second time, you have NOT. So classically, there is no analog of square root of NOT. In quantum mechanics, it is. So it's an example of such a gate which does not exist classically. And then you can, unitary evolution describes dynamics in the space of states. And what is the idea? That you try to find some reasonable way of processing information. So finding such a unitary gate which does something interesting for us. Okay, then you use some matrices. I will not go into details to describe such a dynamics. And in short, quantum computer looks like this. You have here input states. Here you have big unitary matrix, which you can decompose into 2-qubit gates, which are here denoted by those boxes, which couple only 2 qubits, not more. And entire program or processing is here encoded into this matrix, which is represented by a bunch of 2-qubit gates. And at the event you measure something, you perform measurement, you get n output qubits, and this is the result. And you hope that if you have a good idea, good program, from n input bits, you can get some n output bits, which can be interesting. And then the famous algorithm of Shor from 1994 is a device to produce a factorization of a number. And the idea was to show that this factorization is as difficult as finding a period of some function. And then using quantum Fourier transform, show that in principle, having such a computer, quantum computer, which uses a lot of bins, a lot of qubits, you can find algorithm such that the answer measured with large probability will help you to factorize such number, which is important, let's say, for cryptography. Okay, concerning cryptography, look, the key idea is that if we measure quantum state, we change it. But it's a good news, because now if we want to send some secret information, if somebody wants to overhear it, at least he will measure it, so he will change the state, and at least we can detect the action of eavesdropper. So now I will only mention that nowadays we have such a commercial products. Let's say there's a company in Geneva which sells such a commercial product to distribute the information key. It's okay. I think there are several trends in quantum information right now. We study more mathematical foundations and try to find, let's say, best possible algorithms to process quantum information. The key problem is just this decoherence or interaction of the qubits with external world, which destroys information and kills entanglement. And now look at the time scale. So as I mentioned, quantum theory, basically we dated from 1900, starting from the big lecture of Planck. There were postulates of quantum theory, transistor, later. Now in 1964, there was Bell theorem, then Shor factorization. Now the question is whether we'll find proof for quantum computational supremacy. So idea is to find such a problem and such a quantum algorithm which will compute something in a shorter time than classical. This is not achieved yet, and the question mark is when will the quantum computing or useful computing will be confirmed. So for the last 10 years, there is really a great progress and competition. Many companies worldwide put a lot of money to work on it. However, the main question is still open. So there's a nice paper by Gil Kalai, who basically said, well, of course we can do something with 2, 3, 5 qubits. But the question is whether those effects of decoherence will eventually, in an optimistic way, will find some ways to cope with those problems, to get robust quantum computation, to really get quantum supremacy, or just in a pessimistic way, all those noise, effects of quantum noise will induce that all effects will average out and we'll have no quantum computational supremacy. So here, well, the result is unclear. We'll see, I hope, during a few years or maybe 10 years, whether really quantum computation supremacy can be achieved. At the very end, I'm going to finish. Here, as you see, Wawel Castle in Krakow, not far away, only 300 kilometers away. And now look, here is like arrow here points a special place. So my colleagues, mathematicians in Krakow, they formulated such a statement. With probability 1 minus epsilon, the bench Banach talked to Nicodem is 1916, was located in Ita neighborhood of the red arrow. So here is a plate commemorating this discussion. So here you can read in Polish, I will read shorter version in English. Otto Nicodem and Stefan Banach in conversation about mathematics. This bench memorizes the famous meeting with Hugo Steinhaus in the Planck Garden in summer 1916. So maybe you know what happens. Later on, Steinhaus had a position in Lviv, and then he invited Banach, who came here, and then Hugo Steinhaus and Stefan Banach worked in Lviv for many years. Moreover, they used to go and visit the Szkocka Cafe. You recognize the building, which is very close to here. I was very amazed that our hotel is just located just opposite. How it is related to quantum theory? Look, Otto Nicodem survived the Second World War, and in the 60s he was in the US. He wrote the book, The Mathematical Apparatus for Quantum Theory. So even prominent mathematicians took care about mathematical foundations of quantum theory. So to summarize, I think that quantum information evolves rapidly. There are new theoretical ideas and a lot of experimental work is done. And now it's not only quantum theory, but also quantum technology. So we are looking for concrete questions where answers could be implemented practically. So I think there's many open problems, and my main message is that all of you are welcome to contribute to this field. And I will finish showing you again this picture of the bench of Banach and Nikodem, as you see the final version of this picture I showed at the very beginning. So if you ever visit Krakow, it's very close to the center, to the Wawel Hill. It's nice to go there and see it. And here, just mention the famous mathematical journal, Mathematical Intelligence. Also, they were at the cover story. Thank you very much.
Is that your slide, Professor?
Yeah.
Yes, thank you. Thank you very much, Professor. So we learned about Bell steaks and cats, I think.
Yes.
And you were mentioning a quantum computer. So do you think we could make a simpler quantum computer in Lviv? I don't mean maybe 2 or 3 qubits. Do you think that's something we could do, Professor?
Exactly. So this is the point. So
Exactly.
for last 20 years, people start to work with 1 qubit, 2 qubits. To couple them is already something to get some gates. This is possible. But I would not call it really existing computer, but let's say a prototype. And they were done, let's say 20 years ago in other places. So I think this is realistic. But the question is how to cope with decoherence and the problem of interaction with environment to scale the problem, not having 2 by 20 or 200 qubits interacting together.
No, I'm on the photonic side of
Yeah,
things.
yeah,
So,
yeah.
you know, my solution
But,
is going to be
okay.
cold ion traps with lasers.
Okay. Still, you can go to what is the number of qubits you can work with together.
Reasonably, me, I've coded 5 on my.
Okay, so 5.
That's the best.
Okay, so maybe 5. So maybe you can go to 15, maybe 20, but to go to 200 or 300, this is the problem. The problem is, in short, all solutions which are known up to now cannot be scaled in a simple way that if you have 2 such computers, they do not act as a one larger computer.
Oh, yeah.
This is the problem.
Correct. But what I would wonder is for our colleagues here in Ukraine, even experimentally building a 2 or 3 qubit system, it's for education.
Yeah, it's doable.
We should do it here.
Yeah, okay.
Absolutely. Thank you so much, Professor. Thank